But we're talking about splitting fields, and it's a hard topic. And so it's best to think about examples. So let's start simple. We did talk about this example last time, but it would be good to talk about it again. Q square root of 2. Is that the way people say this? Well, usually when they write this, they say the rationals, right? Because Q is the rationals. The rationals adjoin square root of 2. What is this? First of all, is it the rationals and then square root of 2 by itself? No. That's a common mistake. It's a mistake I often thought when I saw this. Okay, I'm going to take all the rationals and just add in the square root of 2. No, many other numbers besides square root of 2 are in here. Beyond the rationals. Infinitely many, in fact. The definition of this is the smallest. That green pen's almost gone, and that was the only green pen I had. The smallest subfield of what? There's lots of things you could choose here. You could pick the real numbers. You could pick the complex numbers. You could pick some other field, actually, even. I'm not going to say. The most common thing to probably pick here is the real numbers. I could say, or the complex numbers, C. The smallest subfield of the real numbers or the complex numbers containing the rationals Q and the square root of 2. But that does not mean that this field is all the rationals and then just square root of 2. It does not mean that. Okay. Without proof, what I'm about to write takes proof. But without proof, I'm just going to say you can describe this set as the set of all numbers of the form a plus b times the square root of 2 as a and b vary over the rationals. But this takes proof. But we're not going to prove it, at least not right now. The set of all numbers that can be written in the form a plus b times the square root of 2 as a and b vary over the rationals. And for extra emphasis, like I talked about yesterday, this is really a linear combination, the set of all linear combinations of the numbers 1 and the square root of 2. I'm not really writing anything different here. I'm just re-emphasizing something. This is a linear combination of 1 and square root of 2, where the scalars are rational numbers. In other words, you can relate this to linear algebra. You can say this is the span of 1 and square root of 2, where maybe we should emphasize the scalars are rational numbers in this notation in some way. Maybe put a Q for a subscript here. Emphasize that the spanning that's going on here is over the rational numbers. The scalars are rational numbers. I'm writing A and B as just pure individual symbols. Of course, being rational numbers, that does mean I could write them as fractions, where the numerator and denominator are integers. I could do that if I want to, but there's no need to, really. And being such a span, and also based on the fact that 1 and square root of 2 are linearly independent as quote-unquote vectors over the rationals, means that this is a basis for this thing as a vector space over the rationals, and that means this is a two-dimensional vector space over the rationals. This set 1 square root of 2 is linearly independent over the rationals. How would you prove that? Why? If you have this linear combination equaling 0, the only way that's going to happen where A and B are rational numbers is if they're both 0. A plus B square root of 2 equaling the number 0, where A and B are rational, implies A and B must be 0. Is that obvious? Well, it's based on the fact that square root of 2 is not rational, because this equation here is equivalent to saying square root of 2 is, I guess it would be negative A over B. And if A and B were both, oops, that's a mistake here. If A and B were both rational, then negative A over B would be rational, and so square root of 2 would be rational, but we know square root of 2 is not rational. Done. If A and B are rational, there's no way this can happen unless they're both 0. Therefore, the set of two numbers, two quote-unquote vectors, is a basis for Q adjoin square root of 2 as a vector space over Q. Okay. The vector space content, which again in the 10th edition of the book, they got rid of it for some reason, is important for understanding this stuff. And it does come up in later chapters in the 10th edition. This is important. You can also say, therefore, the dimension of Q adjoin square root of 2 as a vector space over Q, and so maybe I'll put the Q down here again, is 2. And that would mean any basis for this as a vector space over Q would have 2 elements. You might call this the standard basis, just like we had a standard basis ideas in linear algebra. It's the simplest basis for this as a vector space over this. But this is more than a vector space, it's also a field. Okay, it's sort of confusing. Is it a vector space or is it a field? Well, it's both. When you think of it as a vector space, you're not thinking about multiplying elements in it. You're thinking about representing elements in it as linear combinations like this. Of course, we can multiply elements like this. We can multiply numbers like this, and to verify it's a field, you'd also need to verify it's closed under multiplication and also closed under taking inverses. We did talk about that the other day as well. Let's rethink about that too again. Is it closed under multiplication? So what I'm doing now is not regarding vector space properties, it's regarding field properties. Well, yes, go ahead and FOIL this out. And last times last is B times D times square root of 2 squared, which is 2. We do a little rearranging, and we see that this product can be written in the form some rational number plus another rational number times square root of 2. It's in the right form. It's still in the field. This is verifying closure under multiplication. Closure under reciprocals, multiplicative inverses. We did that the other day as well, but let's do it again. What's the multiplicative inverse of A plus B over square root of 2? Well, certainly in the real numbers, it's 1 over A plus B times square root of 2. But is this an element of the field we're talking about? You got to do a little trickery. Multiply the top on the bottom by this, so that when you multiply it on the bottom, kind of like a complex conjugate, except it's not a complex conjugate, it's a conjugate in this field with the minus sign here. Multiplying this out, the outside and inside terms cancel when you FOIL, right? Because they'd be negative AB square root of 2 and positive AB square root of 2. So you just get the first times first and last times last. And this can be rewritten as this. And it's in the right form. A rational number plus a rational number, subtracting is the same as adding the inverse, times square root of 2. Could we possibly be dividing by 0 here? Could a squared minus 2b squared possibly be 0? No, because it would end up implying square root of 2 is rational if it were. If a squared minus 2b squared were 0, that would be equivalent to a squared over b squared equaling 2, which would be equivalent to square root of 2 equaling a over b. Or at least plus or minus, depending on the sign of a and b. Plus or minus a over b. And if a and b are rational, that would imply square root of 2 is rational. But again, we know square root of 2 is not rational. So that would be a contradiction. So no, we would not be dividing by 0 here. Okay. So just again, summarizing what we've done today so far with this example. This is called Q adjoin the rationals, or excuse me, Q adjoin square root of 2, or the rationals adjoin square root of 2. By definition, this first equality is the definition. This is the smallest subfield of the reals, for example, or the complex numbers, for example, containing all the rationals and also square root of 2. That's the definition. It equals this set, though that takes proof. I'm not proving it. For emphasis, that set could be thought of as the span of two numbers, 1 and square root of 2, where the scalars are rational numbers. It's a set of all linear combinations of those things. And this is a linearly independent set over Q. It's not a linearly independent set over R. The external field for the vector space matters. A plus B times square root of 2 can equal 0 for non-zero real A and B. What's an example? Just choose an A and B so that this is true. Like A is negative square root of 2 and B is 1. Then the linear combination, negative square root of 2 plus 1 times square root of 2 does equal 0. But that's not a rational number. So it's not linearly independent over the reals, but it is linearly independent over the rationals. So it's a basis. It's both spanning and linearly independent as a vector space over the rationals. Therefore, it's got dimension 2. This dimension thing is important for the theory. It's just not just a curiosity here. Okay, it is important. Those are the vector space properties, but again, I wanted to confirm it also is a field. In particular, it's closed under multiplication and closed under taking inverses. And it's definitely closed under addition as well. Add two numbers like this, you can rearrange to keep it in this form. Combine like terms, right? A plus B square root of 2 plus C plus D square root of 2 does equal A plus C plus, in parentheses, B plus D times square root of 2, and both of those are rational as well. It's closed under subtraction. Okay. Can we say more about this? Q square root of 2 also is the smallest subfield of the reals or the complexes in which the polynomial f of x equals x squared minus 2 splits. What does it mean to split? It means we can completely factor it as x minus square root of 2 times x plus square root of 2. X squared minus 2, note, x squared minus 2 is irreducible over the rationals. It's degree 2. It doesn't have any rational roots. That would be enough to show it's irreducible. You actually could apply Eisenstein's criterion as well to this. Take p equal to 2. Does that work? There's no linear term. Well, the coefficient of the linear term, the x term, is 0. P2 does divide 0. It also divides 2, and p squared does not divide 2. So you could also apply Eisenstein's criterion to say this is irreducible over the rationals. But we also know it doesn't have any rational roots. It's degree 2 is therefore another reason it's irreducible over the rationals. And yes, this is the smallest subfield of the reals in which f of x splits. Therefore, q square root of 2 is a splitting field for f of x equals x squared minus 2 over the rationals. And just like with irreducibility, when you say a polynomial is irreducible, you got to say it's irreducible over what field. You have to specify the field. It doesn't make any sense to say a polynomial is irreducible and stop there. I mean, this is an example. X squared minus 2 is irreducible over the rationals. It's reducible over the reals. It depends on the field you're talking about, whether it's irreducible or not. Likewise, q of square root of 2 is a splitting field for this polynomial over the rationals. It might not be a splitting field for this polynomial over some other field. In fact, just for emphasis, let's write down an example. It's not a splitting field for this polynomial over q adjoin square root of 3, for example. What would be a splitting field for this polynomial over the field q adjoin square root of 3? It would be q adjoin square root of 3 and then adjoin square root of 2. That is a splitting field for f of x equals x squared minus 2 over q adjoin square root of 3. Whoa. Does that blow your mind? Well, what's q adjoin square root of 3? Well, by definition, it's the smallest subfield of the reals or the complexes containing all the rationals and square root of 3. How can you describe this in set builder notation? It would be the set of all numbers of the form a plus square root of 3, where a and b are rationals again. But what does that mean about this thing? So it's not clear this is a two-step process. Take the rationals, adjoin square root of 3, and then adjoin square root of 2. It's a two-step process. What's this? Is it possible that this is the set of all numbers of the form a plus b square root of 3, where a and b are in, square root of 2, where a and b are in q adjoin square root of 3? Is that true? It actually is true, yeah. which would mean what? Which would also mean you could write this as the set of all numbers of the form. Oh, should I use different letters? C plus D square root of 3 plus E plus F square root of 3 times square root of 2. E is not the number E. F is not a function. Don't let that confuse you. Where C, D, E, and F are rationals. Running out of paper there, sorry. Which means, I guess you could simplify this. You could say this is the set of all numbers of the form C plus D square root of 3 plus E square root of 2 plus F square root of 3 times square root of 2? Yeah, square root of 6. As C, D, E, and F vary over the rationals. Whoa, it's getting complicated. So again, so this is more than curiosity. This was definitely worth doing. This is fundamental to understanding what's going on here. So reviewing again, we also know Q square root of 2 is the smallest subfield of R in which f of x splits. Therefore, it is a splitting field for f of x equals x squared minus 2 over the rationals. But again, when you say something is a splitting field, you got to say what it's over. If the base field is something different, I pick square root of Q square root of 3, Q adjoin square root of 3. I could have picked something else. I could have picked Q adjoin square root of 5. I could have picked Q adjoin cube root of 2. There's infinitely many choices I could have had for the base field here. And the splitting field for this polynomial in each case would have been something different. Is there another way I can think of this thing here? You also can think of it as Q adjoin square root of 2 comma square root of 3. It also equals that. What's this? Always say this in your mind, what I'm about to say. Silently, but in your mind say, that's the smallest subfield of the reals or the complexes, or some other fields that I'm not going to mention, containing all the rationals, also containing square root of 2, also containing square root of 3. And yes, it does equal all these things. And then, oh, guess what? Vector space. That's the set of all linear combinations of 1, square root of 3, square root of 2, and square root of 6. It's the span of those 4 quote unquote vectors. And those 4 vectors or numbers, 1, square root of 3, square root of 2, square root of 6, are linearly independent over the rationals. You can prove it's hard to prove, but you can prove it. The only way this is going to equal 0 is if C, D, E, and F are all 0 when they're chosen from the rationals. They form a basis for this thing as a vector space over the rationals. This is a 4-dimensional vector space over the rationals because the base has got 4 elements. Something else that's confusing, but important to talk about. Notice the word a or a. This is a splitting field for this polynomial over the rationals. Guess what? It's not the only splitting field for this polynomial over the rationals. There are others. What are they? This gets a little weird. But if you're going to understand the reading and the homework and the exam, you better understand it. Another example of a splitting field for this polynomial over the rationals is take the ring of polynomials with coefficients in Q and form the factor ring where the ideal you are modding by is the the principal ideal generated by this polynomial. That's a factor ring. Since the polynomial is irreducible over the rationals, it's also a field. And in fact, this is a splitting field. For f of x equals x squared minus 2 over q. But it's a weirder splitting field. I mean, for one thing, its elements are cosets, right? It's factoring. Its elements are cosets, not even numbers. But wait a minute. I thought splitting fields have to be field extensions. That's the smallest subfield of the reals in which this polynomial splits. It does contain the rationals as a subfield as well. It is a field extension of the rationals. But is that a field extension of the rationals? Doesn't seem like it because its elements are cosets. Well, you got to look at it in the right way. You got to play the algebraist game of not being able to distinguish two groups if they're isomorphic, or two rings if they're isomorphic, or two fields if they're isomorphic. Not being able to distinguish, okay, it's kind of a joke. Of course, they can distinguish. This has got a subfield isomorphic to the rationals. What is it? Well, let's get into it. What is this? We've talked about this before. This is the set of all cosets that you can form based on this ideal. But remember, this polynomial is irreducible over the rationals. It's got degree 2. If I call this ideal, say, capital A, we've practiced this kind of thing before. X squared minus 2 plus A, for example, is the identity ideal, the zero ideal, which is equivalent to saying x squared plus A equals 2 plus A, for example. And so therefore, if you're thinking about this coset, there's a simpler form of it, 2 plus A. And so higher degree representatives can always be reduced to linear representatives ultimately. Like this, where A and B are rational. Right? We've done this before. And well, what is a subfield of this that's isomorphic to the rationals? How about take A to be 0? Note the subset of this of the form B plus capital A as B varies over the rationals. This is a subfield of this thing, isomorphic to the rationals. Effectively, all the cosets whose representatives are constants. Right? That makes sense. But anyway, the main theme is this is also a splitting field for f of x over the rationals. Again, from the algebraist perspective, it's because this thing has a subfield isomorphic to Q. You can think of this as a field extension of Q.